It's Thursday, Tuesdays and Thursdays. There's only a few of you that make it to class, but that's okay. I'm glad to have you. So Brian talked about glasses yesterday. Anybody have any, you don't have any questions on that? This was my last slide and 2 days ago. And I kind of brought up this question of what's the difference between productivity and competitiveness. And I think I said something about this earlier in the term, but anybody remember what the difference is between productivity and competitiveness? Basically, productivity is how efficiently can you make something, and competitiveness is what can you sell it for. Okay, if I want to give you a sound bite of these things. Productivity is how efficient is your process, your people, everything that goes into the manufacturing operation. Competitiveness is all these other nebulous things like the exchange rate between currency, which has nothing to do with manufacturing. That's determined on some geopolitical level, right? And things. So I was at a meeting once of, I was on the review committee for the National Institute of Standards and Technology in their manufacturing area. And the first guy in the morning gets up and he says, NIST is the Department of Commerce's competitiveness laboratory. And he gives this talk, and at the end I ask a question, I say, don't you mean you're their productivity laboratory? Oh no, we're the competitiveness laboratory. I said, so you're dealing with exchange rates? Well, no. Okay. I mean, competitiveness is what, you know, do you have slave labor? There's lots of places in the world where we still have slave labor. Whether we call them slaves or whether they're, you know, they're treated like slaves, that's all part of competitiveness. Productivity has to do with how efficient is your manufacturing facility. And of course, this is a story about how management always thinks that they're the key to productivity. And if we have time, I'll tell you this story I heard from a vice president of Pratt & Whitney sometime about manufacturing management during World War II. But anyway, today I wanted to talk about steel mini mills as sort of a case study of how you can tremendously increase productivity. You know, we kind of walked through and we said, well, people were making wrought iron and cast iron 400 years ago. It was a person year per ton, okay, and that's dropped down to 20 minutes per ton as a person labor input to making steel today. And some of that was continuous casting and Henry Bessemer melting steel and BOFs and things like that. But another part of this that's been driving this is the steel mini mills. And the steel mini mills came about in the mid-1970s because they were actually Canadians, but a couple of people, well, one of them wasn't. The guy who founded Nucor, Ken Iverson, was not a Canadian. He was just a businessman. But a few people learned that scrap could be had and been hovering for 30 years around $100 a ton for steel scrap. I mean, it might get down to $90 or up to $120, but it's hovering around $100 a ton. And if you remember, I had mentioned the blast furnace hot metal cast iron cost was $180 a ton. Well, they're sort of fungible raw materials in terms of you use steel scrap that comes back through recycling, or do you take virgin ore and put it through the blast furnace and make cast iron? You can put either one of them into the steel refining furnaces if you have the right type of furnace, but this one was basically half the cost. Well, half the cost on something that's 25% of your overall cost in a $500 billion industry could be a lot of money, okay? So these people realized it, and they realized that the only thing that could take 100% scrap was the electric arc furnace. And these things have been around since the 1880s, ever since Westinghouse and Edison gave us, you know, easy available commercial electricity. They also knew that a couple of these people had worked for big steel companies, and they knew the culture in the big steel companies was to do the things the way we'd done it 80 years ago, okay? That was in to just waste money and things like that. So they knew that they kind of looked at electric arc furnaces where instead of 300 tons of steel at a time, you could melt 40 or 50 tons of steel at a time, and it might take you, when they started, about 2 hours to melt it, but you'd end up with steel. And if you used the right type of scrap, that's all you had to do. You didn't have to do all this other refining and other stuff. There were some disadvantages, but they started out saying, we're just going to make rebar, the cheapest value grade of steel. Just a steel bar, doesn't have to have particular impact properties, toughness properties. It's basically a very simple type of material, steel material. And the big companies, they laughed at them. They said, you guys can't produce more than a couple 100,000 tons of steel a year in your plant, and you're selling the lowest quality stuff. Well, this is the whole story of the innovator's dilemma, which is Clayton Christensen's book at Harvard Business School, about your competition kind of taking a big company and nipping at their toes, the bottom of the product line. The big company's trying to come up with new, fancy, better, high-tech, higher value-added product, and these guys are going after the lowest quality stuff, okay? But they could do it with a 20-fold reduction in capital. Today, an integrated steel mill would cost you $20 billion, we noted. You can build a mini mill, and if you remember the picture of the Burns Harbor, Indiana plant of Bethlehem Steel, that was stretched for miles, okay? And this is a mini mill, stretches for yards, okay? And that's a 20-fold reduction in capital. And over here is going to be the electric furnace melt shop, whereas this wouldn't be 25% of the melt shop at a big integrated steel mill. And the rolling mills, well, they're only making one kind of product. They're not an integrated mill that's trying to make 100 different products. They're going to focus on one product to begin with. And they don't care. They're just going to take a small piece of the business. And the big guys laughed at them and thought those guys will never go anywhere. That was mid-70s. I was working for an integrated steel producer, and I remember all the jokes that people were making about the mini mills and how they'd never go anywhere. Well, it turns out today, about half the steel in the United States is made by mini mills. And it's not just the low-end stuff. They just kept on getting better and better and better. So that's part of the story I want to tell you. And I'm going to take an example of Chaparral Steel. Chaparral original plant was in Midlothian, Texas, started by a Canadian who's a graduate of this department. They started in the mid-70s, but I'm going to tell you some stories about the 1990s. And they started out with the rebar business. In 1990, they were down to 1 person hour a ton, which was about half the integrated people at that time. If you looked at my little graph of productivity and stuff. They developed net-shaped casting of structural beams. They decided eventually, after 10 or 15 years, to get out of just cheap rebar. They wanted to upgrade, so they went to steel beams, and they developed net-shaped casting. And here are some pictures of their first continuous cast. They could get a small continuous caster, not a $1 billion continuous caster. This is not the greatest projector in the world, but it'll give you an idea. Instead of a rectangular continuous cast bar, they basically just made the mold, so it had made an hourglass shape. And that was the beginning of an I-beam. You could heat that up and you could turn that into an I-beam. And these are actually Gordon Forward's. He's the guy who was the chairman of this corporation. Here's a bunch of them laying there, and there's the hot bars over there. They just cooled off down here, a bunch of them laying there. And that was around 1990 or a little bit later. Now, they later proved that. They kept on improving the mold design such that this is the continuous cast band coming out of Chaparral Steel. This is where they're flame cutting off their continuous caster, and you now see they've made that little hourglass shape into something now starts to look almost like an I-beam when it's coming out of the caster. And that had a number of important refinements. So net-shaped casting, drove the cost down by 1/3. And concrete, where people were building parking garages out of reinforced concrete, well, now it turns out using steel frame buildings for parking garages became the cheaper alternative. And I used to go around the country and kind of look at parking garages, in fact, and say, oh, that one was built about 1980 because it's steel. That one's built in 1970 because it was concrete. And that was just the change in economics of this type of technology, okay? Another thing they did is four-strand rebar rolling, which this is their earlier product. And one of the interesting things at Chaparral is that they have they're not an employee-owned company, but they have profit sharing. And one of the requirements at Chaparral is one of the production people were required to spend 1 week a year going out with the salespeople and meeting the customers. What a novel idea in 1975 or 1980 to actually have your operations people meet the customers. I remember one guy that I met who had worked for was CF&I, which is Colorado Fuel and Iron or something. Anyway, in Pueblo, Colorado, they had an integrated steel plant. And, oh no, he worked for Armco Steel in Houston all his life. And I was talking to him once, and I asked him, well, have you ever done any benchmarking about other steel companies and how they do things? He says, no, the only other steel plant in his entire 30-year career that he had ever been through was the CF&I plant in Pueblo, Colorado, and he was on vacation, and he passed the steel plant, and he decided he had some time, and he stopped and went up to the gate and said, hey, I work at Armco Steel in Houston. Can I see your plant? Okay? So he got a tour of someone else's steel plant. That was the management intelligence of the integrated steel producers, okay, kind of 1980 or 1985. You wouldn't dare tell anybody about what you're doing because your technology is the best in the world. Your technology is crap, okay? There are other people who have good ideas too, okay? But no, they could never believe something like that. Anyway, Gordon Forward thought it would be good for his operating people to go out and see what other people were doing. And that included not just how to operate a steel mill, but to see what the other parts of the business are. Now, in the old days, the integrated steel mills used to do some of this. When I was hired at Bethlehem Steel, I was what's called a looper. And in the 1930s, if you were in the loop program, and Professor Grant, who was a professor here at MIT, he'd be 100 years old if he was still alive, but he had been a looper in 1935, and a looper in 1935 at Bethlehem Steel meant you were a college-degreed employee, and they would take you for the first year, and you spend 6 weeks in this part of the business, and you spend 6 weeks over in this part of the business. As an engineer, I might have gone to the finance department for 6 weeks to learn how they did it. Some finance person might have gone down to the Ford shop and worked there with hot slag and things like that. You'd spend a whole year as a looper, okay, looping through the business. When I got to do it in 1975, it involved 1 week in the Martin Tower Auditorium having vice presidents give us talks. And that tells you something about how many vice presidents we had. And I remember listening to one vice president of finance get up and explain that, well, in Lackawanna, our Lackawanna plant, we have coke ovens that were built in 1910 and blast furnaces built in 1911, and they're fully depreciated, and it costs us nothing to make steel. Well, they'd have a little question and answer, and I remember somewhere in the questions and answers, I raised my hand and said, I'm sorry, I don't understand why it doesn't cost you anything to make steel because you have old facilities. Oh, well, it's fully depreciated. You just don't understand finance. And he was absolutely right. I was a 24-year-old kid, 25, I guess, in 1975. Anyway, I was a 25-year-old kid, and a couple years later, I took a course at Lehigh University in finance and accounting, and I learned that I didn't know anything about finance and accounting, but I also learned that neither did he. Okay? He was vice president of finance and accounting, and just because something's depreciated doesn't mean there's no operating cost to operating something that's 80 years old. I mean, it's much less efficient than the Japanese stuff that had all been built after World War II because we bombed out everything they had before World War II. But we were still using the old pre-World War I stuff. And the management thought that was wonderful, okay? But that was the attitude of the American steel management of the integrated producers. So anyway, these people at Chaparral, when they were making rolling rebar, they went out and they found that rebar comes in a number of different sizes. Well, they already knew this. Rebar is sized by the eighths of an inch. Number 3 rebar is 3/8 of an inch diameter. Number 5 is 5/8 of an inch diameter. And it goes up to like number 16 rebar, which would be 2-inch diameter bar. And they found there was like a 30% premium per pound for number 3 rebar. And the reason was you could only get so many tons through in the rolling mill per minute, okay? It might be coming through there as hot steel band at 60 miles an hour through the rolling mill, but when it's only that big, you can only put so many tons through per hour. And so they decided they were going to go back and they were going to run their mill faster than anybody else. And they tried for several months to run their mill faster. And turns out there's lots of instabilities when you have hot steel band at 70, 80 miles an hour. It doesn't work very well. So then they started thinking. Now these were what today you'd call empowered employees. And I'll tell you more about that in a little bit, about how Gordon Forward got them empowered. But they started thinking about it and said, well, maybe we shouldn't run faster. Maybe we should run slower. You go in the opposite direction. And this is a picture of a slide from Gordon Forward from 25 years ago that he gave me. Here's the single bar going into the rolling mill at Chaparral. And at this stand, they split it in 2. And so you see 2 coming out. Okay? And then they decided if we did it once, we can do it again. So in this one, you see 2 bars coming in and 4 coming out. Up here, they split it somewhere again, each one of those again. So they started running at half the speed with four times as many strands, and guess what? They doubled their productivity at half the speed. And you didn't run into the instabilities. They took over the 3/8 of an inch rebar market, and the big integrated producers couldn't do any better, and so they took over that market. So that's how different thinking by, if you want to call them empowered employees. So 4-strand rebar rolling, they built a new facility at 0.8 person hours per ton. This is kind of 1990, which was kind of world class. Gordon Forward used to say, when we started Chaparral Steel, it cost $30 a ton for the Japanese to ship steel across the Pacific to the United States. That's just the cost of shipping. If we could make steel for less than $30 a ton labor, there's no way they can compete with us. And that was their goal, to get down to lower labor costs than the shipping costs into this country. Because we're the market, or at least back then we were the market for the world. We still are, but not in steel anymore. They had $450,000 sales per year per employee. And what did that mean? Well, back in 1990, I kind of developed a rule of thumb that I had come up with by looking at some big companies' sales and then dividing by the number of employees, and you'd always end up with something around $100,000 per employee. And you know, you could hire an engineer back in 1990 for $40,000 or $45,000. You could hire an hourly worker for $25,000. You had to have $100,000 of sales, because your product costs you something, in order to employ people. Well, Chaparral had 4.5 times that. Now, this $100,000, you know, I'd look at a company and I'd say, oh, they've only got $75,000 per employee. They don't have very good profitability, okay? I'd look at another one, it might be $150,000, okay? Back in the mid-90s, I was going through the Boeing door plant where they make doors for aircraft. And this is a very interesting business. Purely deterministic. It only takes 1 year to make a door. Now, why should it take a year rather than 3 months? Well, it took them a year, okay? One of the reasons is you have to drill each hole for each rivet about 7 times. There's the original hole, rough hole, and then there's the pilot hole, and then there's the reaming hole, and I don't remember all the reasons, but it's like 7 times a guy with a drill, a hand drill, is putting something through a hole, okay? And it's an interesting business because it's deterministic in manufacturing, and it's the only place I've ever been that's deterministic. You know exactly what your sales are going to be at the end of the year because the orders came in 3 years ago for the aircraft, and you didn't have to start building the doors until 1 year before the delivery because it took 3 years to build the aircraft, okay? So you knew exactly what you had to build, when it was due, and everything else. And I said, well, what does it cost to build a door? They said, well, we don't know. Because it was all internal pricing structure, and the accounting was whatever the accounting was, which probably had no relation to anything. And I said, well, how many doors do you build each year? And they said 750. I said, well, how many employees do you have? And they said 250. I said, oh, then each door costs you $50,000. And they said, how'd you get that? Well, I used my $100,000. You divide 250 into 750, and it's $50,000 a door. Okay, this is not rocket science here, folks, but it's just simple estimation. And they asked some manager, and he said, yeah, that's probably about right. A little bit later. Okay. So when you walk through that door on that airplane, that was 20 years ago, so it's probably the $100,000 door today, okay? But that includes even the little doors that you jump out the window, you know. It also includes the big cargo doors, so there's a variation here. But the door you walk through is about a $100,000 door today, okay? So that's one way to estimate things. But Chaparral had a much better than average sales per employee. The other thing about Chaparral, the rolled steel beams, they took that net-shaped casting and they basically put them in their rolling mills. Before they started doing this, 41% of the rolled beams were imported from Japan or Romania or wherever. After they built their new mill, there were no more imports of structural beams of their sizes, and they were exporting 20% outside of North America. So this was back, you got to remember, this is 1990, when everyone thought that American steel was a dead industry. They had lost their productivity. No, their productivity was still better than anyone else in the world when you have people actually thinking about how to innovate and not terribly, I mean, you go into a dog bone shape as opposed to a rectangle. I mean, that's not that big an innovation. I mean, it's an incremental change. But the big integrated producers, so I'll tell you another story. So I don't even remember what it was, but I remember I only worked for Bethlehem Steel for 20 months. But after about a year, I was working on higher toughness steels and stuff, and I had come up with a process change that would make better quality steel. No cost, just a simple little process change, different way you do it in the plant. And I explained it to my boss, who was an MIT PhD from this department, okay? And he argued with me for a while. He says, why do we want to do this? I said, well, Jim, we make better quality steel, and it doesn't cost us anything. Well, and I finally convinced him, and we went up to the next level manager, who was a PhD from Lehigh University, and he canned it. He says, well, it won't help us sell any more steel. And that was their mindset. All they wanted to know is how to sell another 1 million tons of steel. They could care less about selling better quality steel. And you want to know why they're bankrupt? because they didn't care about better quality, okay? That was their mindset. Anyway, so the new mill had 75% energy savings. They changed this. You saw how everything cooled down there after the dog bone shapes cooled down, and they didn't have to reheat those to bring them up to the rolling temperature. Well, some of these guys in the mill said, oh, it's red hot, or mostly red hot, when it comes out of the continuous caster. Why don't we just go directly to the rolling mill? Or put it through a reheater then without letting it get down to room temperature? Because before they would cast them, cut them, store them out in the yard for a week or two, because you want to have a big inventory in case something broke down and you could keep your other mill rolling. You know. Anyway, they decided we're going to do inline reheating, which they did with, they could go from casting to finished product in 28 minutes without storing things in the yard, less inventory and everything. They ended up, when they did all this with the net-shaped casting, the better one, the more looked like an I-beam, getting very fine grain, all chill cast structure in the casting, and higher tensile strength and toughness. And the interesting thing in the structural steel business is it used to sell 36 KSI steel and 50 KSI steel. And you get a premium for the 50 KSI steel because you had to put a little alloying element and other stuff in it. But in fact, Chaparral, by going to net-shaped casting and inline reheating, and I forgot I should have had data in here somewhere in my notes. They went 75% energy savings, but they went from like 28 passes through the mill to 11, okay? Because you're net shape, near net shape. Tremendous savings, and it turns out what came out had enough strength for 50 KSI. It had plenty of toughness because it was fine grain, and all of a sudden they could sell for the same price 36 KSI or 50 KSI, and that's exactly what they did. They produced one product. You order 50 KSI, we'll ship you this. You order 36 KSI, we'll ship you the same thing. It just exceeds your requirements, and no one's complaining about that, okay? They're getting a better, in fact, if they were smart enough, they'd find order 36, except the certs would say, oh, it's 36, and some auditor is going to come through and say, oh, you're using the wrong quality steel. The architect didn't design it for. In any case, they were making a better quality product. So that's the story of Chaparral. How do they do it? Well, they did it a number of ways. Here's a picture of Gordon Forward, okay? From Vancouver, Canada originally, but now retired in Southern California. This is a new mill they built in Virginia, and you can see coming off their caster, you can see the rolled beams coming off. They started selling steel. Gordon started selling this as recycling. Gordon won some award from Tom Peters, who was a management guru, as the #1 manager in the United States back in the early 90s, okay? And this is a little plot they had. Chaparral had both the steel operations and they had the cement operations, and they had an automobile recycling plant. So their scrap was old automobiles, and they could shred them, and you can shred an automobile in like 60 seconds, okay? Now, before you shred it, you have to take certain things out. You got to take the lead battery out, because the lead battery, you don't want that in the steel. You got to take the seats out, because the foam cushions, you don't want to start putting that into the steel mill. In fact, that's the biggest problem. You see a big mountain, if you go to Chaparral, you see a big mountain of old foam cushions from automobiles. And the other thing is the guys at the recycling plant that were ripping these things out, they didn't make a lot of money on their hourly wage, but they collected the quarters people had dropped under the seat for 20 years, or for 5 years. And those guys Gordon said they were getting about $300 a day in change. Okay, and carry it out. And he had a wheelbarrow to carry out the change. Anyway, they had a cement operation, because one of their philosophies, they put it in Midlothian, Texas, right outside of Dallas, because Texas was building lots of highways. They were going to pave Texas with rebar and cement, okay? Well, it turns out they take the old foam and they'd use it to fire the kiln in the cement plant. That's how they got rid of the foam. So they're recycling that. Motorola would pay them 10 cents a gallon to take the water, the wastewater from their semiconductor manufacturing plant where they had arsenic. It wasn't high levels of arsenic, but they used it to mix into their cement because there's already arsenic in cement at higher levels. So no one could tell that there was an increase in arsenic in the cement when you already have higher levels in the natural stone you're dealing with. And they got paid for the water they were using, okay? So they would take the steel and it'd go to the steel plant. They'd take the foam, it would go to fire the cement operations. Anyway, the whole thing was an energy, they call it energy recovery facilities, but this was their Chaparral's recycling project. This is 1994 on here. What was another thing that, Gordon told me the story once about, they were always looking for a new way. Well, I'll tell you that story in a second. So they were selling steel as recycling because politically that was good for the public. I mean, they wanted to know that this was not a dirty old steel plant. This was a recycling plant that improved things. But one time when they were putting these, firing the cement operations with the foam, some people found out about this and they wanted to know, well, what pollutants are you putting into the atmosphere from your cement kiln? And they had all the data. They knew what was going up the stack in terms of CO and other impurities. And they're trying to figure out how to explain this to the people in Midlothian, okay, to the city council that wants to regulate them. And so they're sitting around the table trying to figure out how to explain this, that they weren't really the great evil Satan company. And one secretary comes in to bring them their lunch or something, and here's part of the conversation. She says, well, is this anything like the automobile? The exhaust from the automobile? And they started thinking about it, and they explained that the pollutants they were putting into the air was equivalent to 2 cars driving past the plant per hour. Well, once you learn to explain it in terms the public could understand, no problem. Oh, we got lots of cars driving past that plant. 2 more is not going to hurt the environment. So Gordon used to go around the country, and he loved to give talks. It's sort of one of his things. He liked to be the limelight of things, and he was a great speaker, or he probably still is a great speaker, except he's probably 90 years old. Anyway, he became chairman of this Chaparral Industries or whatever. But one of the things there were a couple of things that really motivated the people. One is they had profit sharing. You walk through that plant, and every bulletin board had a picture of that week's profits. They know how much they sold that week. They would post it, and every employee, twice a year, every 6 months, they would get a check, depending on how efficient they had been. And so people wanted to be efficient. When they were thinking about some new piece of capital equipment, these guys weren't figuring out, like at Bethlehem Steel, what's the biggest Cadillac we can buy, okay? And then you approve that budget. They were trying to think, can I get by with a Yugo? Or can I buy a used Chevrolet to do the same thing? And because they knew that was part of that was their money, okay? So they took personal interest in it. Now it turns out I was part of a study group as part of the LFM project a number of years ago, back in the early 90s, on Chaparral. And Steve Wheelwright, who was professor at Harvard Business School at the time, and I were assigned Chaparral Steel. And so we went down and spent a couple of days at Chaparral with Gordon, and there were a couple of things that came out of that. The first day we were asking about, we were supposed to be doing a study on how they would run projects. Okay, what made them different? And we were taking 5 companies. Some other people were doing, I think, Kodak, and someone was doing Hewlett-Packard, and there's a book over here that talks about the 5 things. But we had Chaparral Steel, a mini mill, and we were supposed to write up something about how Chaparral ran projects. So we met with Gordon the first morning, and I said, well, if you have an unsuccessful project, who gets the blame? Okay? And Gordon, he didn't understand what I was asking. I was like, oh, fine, okay. And we go somewhere else, and then the next manager we're talking to, I said, well, how do you apportion the blame? And they didn't understand what I was talking about when you had an unsuccessful project. And I asked the question 3 or 4 times that day of different people, not in front of the same person who would refuse to answer it before. How do you apportion blame? And it turns out I'd always get this answer. They didn't, what do you mean? And that night, I'm thinking about it. What is going on here? Okay, because I knew in every other company I'd been through, whether it was Bethlehem Steel or whether it was Boeing or whether it was General Motors, if you had a failed project, at the end, someone got the blame, right? And that night, I realized that the culture that Gordon Ford and others had started at Chaparral was not who's going to get blamed if this project fails. It was what you got blamed for is, what have you done for me lately? If you hadn't tried to do something new and different in the past year, you were downgraded. You would not get as good a raise. They didn't care if your project failed because Gordon knew that not every project was going to be successful. What you got blamed for is if you didn't take some risk and try to do something differently during the past year. If you went a couple of years without trying to do something, you probably get fired at Chaparral. Completely different culture, a culture looking for innovation. So Chaparral had a number of things. The other thing, so we went to the corporate dining room, and Gordon was very proud of his corporate dining room. At Bethlehem Steel, I told you we had one of the most expensive research laboratories in the country, built in the mid-60s, $600 million. It'd be billions and billions today to build this Homer Research Labs up on top of the mountain overlooking the Bethlehem Steel plant and Lehigh University. They've since, when Bethlehem went bankrupt, they basically gave it to Lehigh University, and so now it's a Lehigh University facility. But they had a beautiful, beautiful cafeteria, and I would go up there sometimes to eat my lunch in the cafeteria, overlooking, just overlooking from the top of the mountain, looking out over the veranda and stuff. But we passed the executive dining room. In the executive dining room, I saw strawberries in there as I walked past, the size of tennis balls, okay? I've never seen something. I mean, today, you actually see some of these things at Costco and stuff. But back then, this was something that my eyes bugged out to see this type of food that was in there. Of course, I never got to eat in there. The guy who was vice president of research was an MIT grad from this department, and the management took care of themselves at Bethlehem Steel. In the 1930s, when Bethlehem Steel was losing money, 6 of the top 10 paid executives in the United States worked for Bethlehem Steel, and they were losing money. And Eugene Grace got a multi-million-dollar profit because it was all based on number of tons poured, not profit made, okay? I lived out near the airport. You drive by and you see 3 or 4 Gulfstream jets, and these people would basically fly these to Florida on the weekend to play golf, okay? This was, if you were top management at Bethlehem Steel, you were treated like a king. And these guys thought that they were, and there weren't any women, by the way, in this group, okay? It was a pretty sexist organization. Anyway, so Bethlehem had this terrible culture, basically, of things. And at Chaparral, it was different. Chaparral, we had some folding tables. We had some steel case chairs, not as fancy as these, okay? Just regular old steel case chairs. And they brought in some Texas barbecue, and we ate from paper plates and plastic forks. That was, as Gordon would say, that's the executive dining room at Chaparral. Because, first of all, the employees, if they saw Gordon eating fancy, they'd know, that's my money, okay? profit sharing. That's my money you're spending. Gordon had to set the example, but Gordon thought it was funny because he had seen these big palatial integrated steel facilities where they treated the management like kings. I saw it. The fanciest resort I ever saw was in 1991 when I had to give a talk to the presidents of the American Iron and Steel Institute, the presidents of the steel companies, on why steel was important. It was in Orlando, Florida, one of the first fancy gated resorts, you know, probably costing $1,000 a night, but these guys are not paying for it. So the type of things that people pay for. But that was true of lots of companies, lots of big companies, whether it was Kodak or Alcoa or Bethlehem, big corporate waste, so far as that goes. Okay, any questions on that? So the mini mills now are over 50% of the U.S. steel production, and they're much more efficient, both in terms of capital cost of equipment, and they can now produce steel of similar quality to the integrated producers at much lower cost, and they're profitable. Okay, let's talk just a little bit, I only have one slide on it, about reinforced concrete, because we're talking about structural materials. Reinforced concrete is really a composite material, but it's when we talk about the billion ton per year club and we've got stone and then we've got concrete, well, the best concrete is reinforced. And this is a modern reinforced concrete structure in Germany, okay, pretty fancy building. This is people actually pouring the concrete onto the steel rebar. You don't have to have steel rebar, but you can actually see on the tensile side of this beam, you've got the steel bars on the tensile side. You don't put them on the compression side because concrete's fine in compression. It's all fracture mechanics here, right? You know, the Griffith equation and stuff. So it has to be about 5 or 10% cross-sectional area of steel compared to concrete, because steel's about 10, 20 times stronger than concrete. Concrete typically after 30 days after pouring has about a 3,000 psi tensile strength. Steel's 30, 60,000, pick your number. And they also do all kinds of fancy things like pre-tensioning these rods now. So they put compression in the whole thing. They actually, as they're casting the concrete in some form like this, the big hydraulic jacks that put tension in the steel. So when you cast the concrete and then you relieve, you take the hydraulic jacks away, the steel contracts and puts everything into compression. So you keep the concrete in compression. Those are little tricks. This is the Harvard football stadium. Anybody know why it's here? In 1983, it was named a National Historical Landmark because it's one of the first major reinforced concrete structures in the United States. It's like 1900 or something. You can look it up on Google if you want. Okay? So reinforced concrete, 4.2 billion tons a year is concrete. It's not all reinforced, but it's a very low-cost material, and people have learned to engineer with a very brittle material. I told you the structural materials course. I tell you steel is a wonderful material because it's got toughness. Most metals have some toughness. But guess what? We got brittle concrete, which outsells on a tonnage basis all the metals in the world by a factor of 3 or 2.5. Okay? So we've learned to deal with brittle materials. And Brian talked about crown glass, and I won't do that. He probably talked about fiberglass manufacture and plate glass manufacture and float glass manufacture and strengthening of glass. And strengthening of glass, you talked about all these, right? You got thermal tempered glass, mechanical laminated, and chemical ion exchange. Someone said they wanted to do the Prudential building for their talk, and they used chemical ion exchange, tied up about a year's capacity to make chemically tempered glass. And we won't go through that, but I did want to talk a little bit. Did you actually even show them the willow glass? Okay, so 2 years ago, Corning came out with something called willow glass. Very thin glass sheet. It's 100 to 200 microns thick. You can buy it in 2 sizes. That's 4/1000ths of an inch, or slightly more than one human hair, or 8/1000ths of an inch thick. You can obviously bend it. I wouldn't try bending it in a compound curvature, in two directions, okay? But extremely strong and scratch, well, glass is scratch resistant anyway. You can't even scratch it unless you got a carbide or a diamond tool. I can take a steel knife, a hard knife, and I won't scratch that glass if I take a sharp knife up against that steel or that window glass. Glass is significantly harder. But the problem, did you tell them about the problem of corrosion of glass? Okay. Most glass that we know of has a significant decrease in strength over time. This is duration of stress versus the bending stress. And glass starts out at 14,000, is that megapascals? I can't see it from this angle. PSI. 14,000 PSI. About as strong as aluminum, okay? Regular aluminum, not super aircraft grade. And within 1 second, it drops down here. And within an hour, it drops down to 1/3 of the original value, a day, a week, and a month. It's down to 1,000 PSI, not as good as most plastics, okay? Now, Bob Rose, my old thesis advisor, when he was teaching 3091 30 years ago, or 50 years ago, I don't know how long, had to be 40 years ago. He would stop at the Sylvania plant up here in Danvers. He lived up in Peabody. And he would pick up freshly made light bulbs from that morning. He'd come in and at the 11 o'clock lecture in 3091, he would take the glass light bulb and he'd throw it against the wall and it would bounce. It wouldn't fracture. You wouldn't dare do that with a day-old light bulb. What happens is when you first make the light bulb or form the glass, it's got a very smooth surface, no small flaws. And remember, the fracture mechanics of glass is such that a few, 100 micron flaw and all of a sudden you've lost 90% of your strength. Well, it turns out the problem is the sodium and potassium oxides in the glass are attacked by the humidity in the air. So if I want to make something out of good fiberglass, I got to make my glass fibers and coat them with that plastic within an hour or two, or I'm going to lose most of the strength of those fibers. When those fibers first come out of the fiber machine, they're as strong as steel. They have no defects. But once the humidity attacks them, then I have little flaws, surface flaws, and fracture mechanics tells me I'm going to have lousy strength. So what did Corning do? Well, the first thing when I looked at this a few weeks ago, they use alkali-free borosilicate glasses. Alkali-free. No sodium oxide, no potassium oxide. They get rid of the corrosion problem. Okay? What else do they do? I will bet you money, because I know something about how Corning makes the flat panel display glasses for laptops and TV screens and cell phones and stuff. This is a cell phone thing, which they call, you can look it up. It'd be a good project, a presentation. I will bet you money this is at least 3 layers. Just like Corning ware, the cookware, it's 3 layers of glass. It's a laminated glass. Top layer and bottom layer like a peanut butter and jelly, peanut butter sandwich. The middle layer is going to be a different coefficient of expansion. When you pull these things off like a plate glass manufacturer, just rolls of these sheets of glass, put them together, 3 layers, you end up with, when you cool it down, compression on the surface and tension in the middle. So you can scratch it. You can have moisture attack it, but it's in compression. And when you're in compression, that's what this is all about. If you have compression in your glass, you're going to be stronger, and the critical flaw size is going to be much larger. This is not the critical flaw size, but basically this is laminated glass where you keep the center in tension and the surface in compression. I will bet you money, I don't know what willow glass is, other than willow glass tells me it's alkali-free. That means no sodium and potassium attack by moisture, and I will bet you that they have done the same thing they've been doing for 60 years in big thick pieces of Corning ware, cookware, where they laminate it and give you favorable compressive stresses. And now, other processing technology which I know about for displays for the last 10 years, they have taken to the extreme of very thin, okay? And now, if you're going to have a backsplash in a kitchen, they paint the back of the glass, and now you have a hard surface, very thin. You just put it right up against the wall, and it's an architectural marvel, okay? So that's, okay, I've run over a little bit.